As we experience a record number of twisters, and cities around the world once again saw the hottest day ever on record, debates rage on how to cut fossil fuel emissions. People are crying, too little, too late. The daily updates of weather-related disasters seem to be leaving more and more people with a sense of helplessness. However, there's a new developing field of science referred to as climate restoration that's gaining traction. Climate restoration aims to return our climate to a stable and healthy state as it was before the Industrial Revolution. But people are asking, will removing excess greenhouse gases already in the atmosphere take pressure off those that need to reduce fossil fuel emissions? And how safe, financeable, and realistic is it? We'll be interviewing some key voices. But first, some important sports news.
What is your vision of the future? A bright and happy world of comfort and meaningful progress? Or a dark and dysfunctional world where you just try and outlive the next catastrophe? For many people, there's a vast chasm between what they hope the future will be and what they think the future will be, and that the stories of catastrophe on the news may one day soon be their own story.
It's hard for me to be excited about the future, and I think I've realized a lot in my life that if people are still getting Instagram followers and can still get 2-day delivery from Amazon, they're okay, they're happy, they don't care about anything else.
I think I'm scared, but I'm hopeful. I walked pretty blindly through the world, I feel like, for most of my life, kind of almost paralyzed by fear because I see everything going on around me, and for the most part it hasn't really hit me locally yet.
Never before in the history of humanity has the total population of the planet been affected by the actions of the few. Our climate is in chaos, and it's only going to get worse. This is a story about a group of people from across a wide range of countries, professions and talents, all working towards returning our climate to a state where all life can thrive. So what moves us to action? And what holds us back from responding to a crisis that will dramatically affect our own lives, but isn't part of our immediate experience? For many, the biggest thing holding us back is our comfort. For others, it's the paralysis of feeling they have no voice or power. Many put profit and convenience before consequences, but more and more are at the receiving end of a climate in free fall. Amidst the growing climate chaos, we explore the new evolving science of climate restoration, the removal of methane and carbon dioxide from the atmosphere. If climate restoration is combined with a serious reduction of fossil fuel emissions and the restoration of our ecosystems, we stand a real chance of returning our climate to a state where all life can thrive.
Climate restoration is the goal and associated actions for restoring CO2 levels that humans have actually survived long term.
To achieve this, science is vital, but it's not enough on its own. We meet with renowned scientists, strategists, entrepreneurs, supporters, activists, and catalysts, all working towards the same goal.
I will continue working until I'm laid out in a coffin to see that we can create a manageable future.
I think there's too much focus on the problem, which is climate change, which is a good thing, but if you don't have any support for the solutions or any excitement for the solutions, that's where a lot of things can go south.
You have to be an optimist to be a climate scientist. Otherwise you couldn't get up in the morning and couldn't work in this business.
Restoring the climate has never been just about the science. If we're to succeed, it requires support from all sectors of society to listen, recognize the challenges, collaborate, and move forward to an achievable goal. Success is about having an objective and being focused on where you want to be.
My background is originally in engineering and in a lot of different impact-oriented projects. But as I started learning more and more about the climate crisis, it became clear that it was one of the most fundamental and challenging challenges that we faced. and was the underpinnings of so many of the other things that I personally cared about.
Peter Fikowski is a physicist, engineer, entrepreneur. He's also the co-author of Climate Restoration, the only future that will sustain the human race. He believes that we already have the basic technology to restore the climate to its original state, and has co-founded a number of organizations in pursuit of this.
People talk about a wake-up call on the climate, and they want to wake people up. And to have a successful journey, you need two things. You need to know where you're starting, and you need to know where you're headed. And people are sort of aware that things are in a disaster state right now, but until we really built up climate restoration, people weren't clear where we're going.
Today, the science and a little common sense is telling us that even if we reach a point where the amount of CO2 we put into the air is balanced out by nature's process of absorbing it, known as net zero, we're still in for major problems. The Paris Accord, the US Inflation Reduction Act are positive steps working towards achieving net zero by 2050, but it's not nearly enough, and these agreements are already being eroded. So where we stand right now, we being all life on Earth, is at the edge of a precipice, a tipping point that may be irreversible without immediate intervention.
You see, the elephant in the room is the carbon dioxide that we already have in the atmosphere. Now, you see what's going on around us. You see all these extreme weather events, people suffering all over the world from floods, from droughts, from heat waves. This is all due to the CO2 in the atmosphere that we already have. And this CO2 in the atmosphere is not going away anywhere by itself. It's going to stay there. So if we stop emissions right now, this very moment, the series of extreme weather events will continue. That's the new norm.
To understand how we may be able to solve the climate crisis, you also need to understand how bad things really are. And to do that, we have to go back around 800,000 years. A blink of an eye in geological terms, but long enough to recognize the steady pulse of a self-regulating system. Here at the US Geological Survey Base in Antarctica, scientists drill and retrieve ice cores to learn about how our climate has changed over thousands of years. It was here in Antarctica in 1988 that a joint Russian-US team of scientists took ice core samples throughout the depth of the East Antarctic ice shelf. At a depth of over 4 kilometers, it's the deepest known ice pack on the planet. Each year's snowfall and dust deposits encase bubbles of air in the ice, providing an accurate record of climate conditions going back over 800,000 years. What the data showed was a repeating cycle of approximately 100,000 years where the climate went from warming to cooling. As CO2 naturally increased in the atmosphere, climates warmed, and then as CO2 was naturally absorbed, the temperature cooled. If you look at the last 12,000 years, you'll see a time of climate stability, where CO2 was around 270 parts per million, and this is what allowed humanity to flourish. Apart from the occasional catastrophic volcanic blast, earthquake, tsunami or flood, life on planet Earth was pretty good, climatically speaking. But then, around 1760, came the Industrial Revolution, powered by fossil fuel, leading to the fastest increase in CO2 levels in the planet's history. Today we're at around 423 parts per million of CO2, and since temperature records have been annually recorded, the average temperature has risen close to a critical 1.5 degrees of warming. Restoring, repairing and maintaining ecosystems and a real reduction in fossil fuel emissions are essential to our survival. But if a repaired climate is the destination, the only way of getting there is by also removing the human-made emissions that have built up over the last few hundred years. And to achieve this, Scientists have been researching methods on how nature deals with carbon dioxide and methane. Some of the methods being developed include seaweed permaculture, where sargassum and kelp, two types of seaweed that can absorb large quantities of carbon dioxide, are being harvested and converted into commercial products, many of which can replace animal and fossil fuel products such as fertilizers, emulsifiers, and vegan leather. Research is also being done on baling the seaweed and depositing it into deep, sparsely inhabited ocean areas. Ocean iron fertilization is a process that mimics how every year winds blow iron-rich sands from the Sahara Desert across the Atlantic Ocean. Along the journey, millions of tons of the sand drops into the ocean, fertilizing the barren Central Ocean, creating phytoplankton and zooplankton that can capture enormous amounts of carbon dioxide before being eaten or dying and sinking to the bottom of the ocean. Artificial limestone manufacturing is a process where waste carbon dioxide is combined with calcium from waste materials such as cement from demolition sites and converting it into a form of artificial limestone that can then be used as a carbon-negative material in the construction industry. Accelerated or enhanced methane oxidation. Around 1/3 of climate warming is due to methane, which is far more potent than CO2. Nature continually oxidizes methane in the atmosphere, breaking down this superpotent greenhouse gas into water and CO2. Scientists are now exploring ways to replicate the process in an accelerated way. Methane removal is essential if we're to reduce and stabilize global temperatures. Out of each of these technologies, methane removal is the focus of this story, because in terms of slowing down climate warming, it offers the most immediate possibilities. But what is methane, and why could it play such an important role in restoring the climate? One of the top scientists working in the field of methane and methane removal is Dr. Renaud Richter.
So methane is a greenhouse gas, much more powerful than carbon dioxide. On 20-year basis, it's 86 times more powerful. And what is attracting in methane is its short lifetime, because it's only between 8 and 12 years lifetime. So we can act on methane, and we should act on methane, because right now the global warming due to methane is 0.5 degrees Celsius, and the carbon dioxide is only about 0.8. So methane is really the second most important greenhouse gas, and acting on it, we can reduce temperatures.
Spark Climate Solutions, a California-based organization, is working to accelerate research on methane through funding, support, and collaboration with scientists from around the globe.
Methane comes from a wide variety of anthropogenic, human-caused sources, as well as natural sources. Human sources are different sections of agriculture, different leaks from gas and oil systems, and also different types of waste, landfills, wastewater, etc. We've also always had some natural emissions from things like wetlands and termites. But the overall methane emissions have dramatically increased due to human-caused activities, both human-driven sources of methane, as well as now climate changes that are accelerating some of those natural sources.
Methane now is in everybody's gun sights, because the effort to reduce methane can avoid nearly 0.3 degrees Celsius of future warming by the 2040s. So it's now the single biggest and fastest way to slow future warming.
The Titanic didn't see the iceberg coming until it was too late. But in our case, the ever-growing impact of climate change is predictable and inevitable if we don't accelerate research on removing CO2 from the atmosphere. However, an issue that could eclipse CO2 in the short term is the possibility of methane reaching a tipping point and creating a methane burst. It happened once before, over 200 million years ago, and is considered to have been responsible for the extinction of around 90% of all life on Earth.
Here we are, we're in a tsunami zone. We are routinely preparing for a worst-case disaster scenario here in Port Townsend. We have no preparation for a worst case scenario of a methane burst.
According to a report by the International Energy Association, methane emissions from the energy sector could be underreported by as much as 70%. So the need for research into methane removal alongside methane reduction becomes more important as each day passes. The world's 5 largest methane emitters are China, India, the United States, Russia and Brazil. Together, they're responsible for close to half of all man-made methane emissions globally. And then there are the unanticipated events such as global wildfires, the sabotage of the Nord Stream gas pipeline in the Baltic Sea that released over 500 kilotons of methane in 1 week, the ongoing destruction from the war in Ukraine, and the Soviet-era drilling accident 50 years ago in Turkmenistan that led to a methane-releasing crater that burns to this day, having released an estimated 3.7 million tons of methane into the atmosphere.
I think one of the main barriers is there's no price on methane. Companies and people don't pay anything for the methane we release into the air. An oil and gas well that leaks gas into the air is free. So we need to change that and put a price on methane in the same way that we need a price here in the United States on carbon dioxide pollution. As long as greenhouse gas pollution is free for companies, there's no incentive, no financial incentive for them to act.
If methane leaks were visible, the outcry would be enormous. But as an invisible, odorless gas, most companies seem unmotivated to address their leaks, which have consequences for all life on the planet.
We've got feedback loops that are happening right now in the atmosphere that are essentially creating a runaway feedback loop of methane levels rising. Simultaneously, 40% of all methane that ends up in the atmosphere is coming from so-called natural sources, such as this wetland behind me. Unfortunately, both the 60% coming from man-made sources and the 40% coming from natural sources are increasing. And the fear is that that 40%, the natural sources, that we may have triggered a feedback loop that could exceed the 60% now that we see coming from man-made sources of methane, and we could get a sudden burst of methane in the atmosphere, which would be, simply put, catastrophic.
So this feedback loop, where the warming climate is causing more natural methane to be released, which in turn is also contributing to temperature rise, is no more apparent than in Siberia and Alaska, where the consequences can be seen growing by the day.
So this path that I'm on used to be boreal forest with spruce trees, birch. Beneath me and under the ground there are massive blocks of ice. We call them ice wedges, and those blocks are melting, and because of that melt it's turning into a mucky puddle. In the next year or two, this puddle is going to become a pond that is really the birth of a new thermokarst lake. It will grow bigger and bigger, and this environment can produce a lot of methane gas. I'm pretty concerned because this is my only way so far to get to my study site. So perhaps instead of walking, I'll be taking a boat in the future.
The Arctic Circle region has been heating up for the past 20 years at roughly 4 times the rate of the average for the whole planet, which means that today the Arctic Circle is at 3 degrees above the pre-industrial level, and therefore the Arctic Circle tipping points have now irreversibly tipped without interventions. Now what does this mean? And I think it's important that I spell this out. What happens in the Arctic Circle impinges on the entire world and is already doing that. The extreme weather events we're experiencing around the world today are heavily driven by what's happening in the Arctic Circle region.
Compared to the 1981 to 2000 average, the March Arctic sea ice pack had lost about 1 million square kilometers.
When permafrost ground is frozen, it contains massive amounts of carbon, 1,500 billion tons. That's 150 years worth of current human fossil fuel emissions, all frozen in the ground. And it's frozen in the forms of dead plant and animal remains. So when the permafrost warms and thaws, it's like opening a freezer door and giving microbes a huge feast. All that carbon that's been frozen for thousands of years becomes food for microbes that decompose it. And when it's under waterlogged conditions, like the bottom of a lake, oxygen cannot get into the sediments, and so the microbes make methane. Methane is about 30 times stronger as a greenhouse gas than carbon dioxide. So there's a big concern, a big implication for permafrost thawing and forming thermokarst lakes.
We can no longer take for granted the seasons and the way of the land. The world is changing, and the effects of thawing permafrost can be seen throughout cities like Fairbanks, Alaska. Once healthy forests are collapsing into newly formed thermokarst lakes. But to get a clear picture of what's really going on, it helps to see what's happening below ground. The Cold Regions Research and Engineering Laboratory permafrost tunnel in Fox, just north of Fairbanks, Alaska, was excavated over 40 years ago by the US Army to research tunneling and construction techniques in permafrost. Today, it remains an active research lab where you see firsthand how animal remains and vegetation that died up to 40,000 years ago remains frozen in time. But all that is changing as the ground warms up and the frozen vegetation begins to rot and release methane. The large bodies of trapped frozen water are also starting to thaw, leading to the collapse of surface ground and the formation of new lakes.
What we are seeing is a disaster in the making. If all of that methane was emitted, let's say over a 20-year period, global temperatures will rise by 5 to 8 degrees centigrade. And when would that happen? It has already begun to happen on a smaller scale. My fear and our fear is that in a few years' time, because this heating of the Arctic Circle region is still continuing, this may release rather quickly.
Right now, we're chasing a fast problem with slow solutions. Indeed, we're chasing an accelerating problem with slow solutions. So slow success is no success.
So what are the options available to reduce and remove methane from the atmosphere in quantities that will make a meaningful difference to the climate?
Anthropogenic methane emissions reduction is a really huge and important part of the overall methane problem and needs to be priority one. However, natural methane emissions are also increasing, and we have fewer controls over those emissions. Plan A is always to mitigate overall climate change in order to mitigate those emissions in the first place. But at this point, we need a plan B as well. And that plan B is starting to understand if there might be ways that we can help to remove that methane from the atmosphere more quickly than it naturally would break down on its own.
But amongst the profound challenges that methane presents to the climate are some real opportunities due to its short lifespan of up to 12 years, as opposed to the thousands of years that CO2 takes to naturally break down.
The reason that methane is so short-lived in the atmosphere is that it has a number of ways that it naturally breaks down, and that happens in the air and that also happens in soils.
Nature's ability to effectively remove methane from the atmosphere has been overrun by the sheer volume of methane being put into the atmosphere by human activity. But what if it's possible to mimic and accelerate what nature does? Taking a lead from a process that takes place in nature, the basic concept behind the iron salt aerosol process is that if iron-rich particles containing chloride are released into the atmosphere, sunlight will irradiate them, producing chlorine radicals. These, in turn, can drive reactions that convert methane into far less damaging carbon dioxide and water.
the natural methods by which methane is removed from the atmosphere is just by oxidation. One molecule of methane plus oxygen will give one molecule of carbon dioxide plus water, vapor. And of course the chemical reactions are more complex than that. But our goal is just to speed up these natural oxidation processes with great benefits for climate.
But what nature achieves with ease can be deceptively difficult to replicate. However, here in Copenhagen, Professor Matthew Stanley Johnson is part of a team that has brought the possibility of replicating and accelerating one way nature breaks down methane a step closer.
We're on our way to the Department of Chemistry at the University of Copenhagen, and we've done some very nice experiments showing how this iron chloride mechanism is working. I think it's the cutting edge of climate science right now. There has certainly been a lot of focus on carbon dioxide and, justifiable focus, but we can't solve the climate problem without addressing methane. There's two things that we need to have an impact on methane. So these two ingredients are iron and chlorine. And what we've done is to find that you can have the iron from mineral dust in the atmosphere and the chlorine from sodium chloride that you have from sea spray. So what we've done in the laboratory is to show that when these two elements come together, you have iron, you have chlorine, you form iron chloride, and this is able to absorb normal sunlight and produce reactive chlorine atoms, and it's catalytic. This means that it's a rapid process that can produce enough chlorine to have an impact on methane.
But how could this research ever be developed at scale to help address the growing methane problem? A breakthrough came when scientist-innovator Martin van Harpen came across a data set that was a 20-year-old mystery. It was readings from a weather station in Barbados that showed a drop in methane that couldn't be explained. Aware of the Sahara dust movements and the lab work involving iron and chlorine, could this be a smoking gun that showed how nature was able to accelerate a process of breaking down methane?
A while ago, I was looking at that iron salt aerosols topic. That something like this is happening in the lab. And I was hoping to find evidence of this in nature. And then my eye caught some data from Barbados, where there was a CO isotope being depleted. And that article was saying that it must be due to the chlorine, but they had no explanation of how that chlorine could exist.
There's a lot of dust coming from the Sahara Desert, and this is spreading throughout the world. It comes over to the Caribbean, it goes to the Amazon, it goes to Northern Europe, where we are right now. But what we've done is to show that when this mineral dust descends into the marine boundary layer, it mixes with the sea spray aerosol. This has an impact on methane. So it's the natural mineral dust combining with sea spray and sunlight that's generating reactive chlorine that impacts methane.
Then what I noticed is that aligned with the Sahara dust episodes as they arrive in Barbados. Maybe the Sahara dust is making chlorine and it's causing this effect in Barbados. In the meantime, we have proof, because what we did is we took a supercomputer and had it calculate the total atmosphere. Then predicted indeed that the effect in Barbados can be due to the Sahara dust as it arrives there. And this is a 20-year-old mystery that we now have solved. So now that supercomputer is predicting a cloud of effect across the North Atlantic. It's saying that there should be the same effect also in Cape Verde, a little bit in Tenerife, in Barbados, and even in the Amazon forest. That's why we are measuring in all those places. But what we really would want is to measure the air as we go through from north to south through the cloud of dust.
A major barrier to this line of research on methane has been that the amounts of methane being broken down in the atmosphere are so minute that they aren't measurable. So, an innovative method of identifying an element with a unique signature only present when methane is broken down was applied, allowing them to move forward with the research.
So we have the methane, a greenhouse gas in the atmosphere, and we want to see how it is removed. We are looking especially at one specific removal pathway, which is by chlorine. Chlorine is a very active gas in the atmosphere that reacts very quickly. And now, chlorine in a certain environment removes so little methane that no one can measure it. There's also so little chlorine that no one actually can measure how much is there. But the nice thing is it forms a product that is carbon monoxide. And on the carbon monoxide, the methane that is formed via this reaction has such a special signature, we call it an isotopic signature, that you can measure really very small amounts of methane that have been removed by chlorine and form carbon monoxide. So we're looking not at methane, but at carbon monoxide. We can actually find out how much was removed by this pathway. And that's what we are now trying to set up in different places of the globe.
And that's where the ships come in. So I reached out to Berend van der Kraats and asked him if he could somehow help us design an experiment or a way to get to these samples.
Yeah, so the scientists actually request me for samples in a certain area over the ocean. I know where the shipping routes are. We reached out to the different ship owners who operate there, actually bringing the scientists into contact with their environmental department, letting the scientists explain what they're doing and why it's important and why they could be of added value. Then we get contacted via that environmental department to the ship manager. The ship manager just knows where his ships are at what period of time when they are pulling into port.
Yeah, what I understood, it's about the reduction of methane in the atmosphere, and that there was a thesis how this could be reduced, and that for this purpose he needed some samples of air in the middle of the ocean where there was Sahara dust floating about. And our ships, they actually go on these routes where the Sahara dust is, and well, here we said we can do this. We can take samples for you.
We send the samplers and the flasks over to the harbor, to the port, and then the ship goes off he goes.
The groundbreaking research on how methane is affected by iron-rich dust clouds shows how vital collaboration is. This would not have been possible without a partnership between shipping companies, scientists, funders, and visionaries. Science may be at the foundation, but without broad collaboration, it remains nothing more than an idea.
I do this because I find it very interesting to see how the analyses which I do here, what they can be analyzed to demonstrate. We do the samples, and I'm in front of the sampling machine with the bottles.
Once back in the port of Rotterdam, the air samples are rushed over to Utrecht University in the Netherlands, where the complicated task of separating the telltale carbon monoxide begins.
So my responsibility in the lab is to take measurements on our flasks, so taking isotope measurements of carbon monoxide and methane in the atmosphere. And then once we have those measurements, we prepare the flasks to be sent back to the field so that we can get good, clean samples for the next time.
So the challenge that we always have in our laboratory, we make these measurements of the gases, and to do that we have to separate one gas, whatever gas it is, in this case now carbon monoxide, we have to separate it from all other gases. But there's only one molecule in 10 million molecules is carbon monoxide. So we have to get all the other 10 million molecules out, and that's why it takes us years to build such a system.
And the first data that is now coming in is really seems to confirm what we think. Because as the ships are going into the dust plume and out, we see the signal go up and back as they exit the Sahara dust. So it really looks like we've got something here, but we need more data still to fully be sure that it's indeed proof of this effect.
We're in the midst of a serious growing emergency. Finding the balance between caution and speed is complex. We're running out of time, but the risk of getting it wrong and causing irreparable damage on a global scale is real.
So if you're under certain circumstances, iron chloride could actually make the problem worse and give you a higher methane lifetime and a higher methane concentration. On the other hand, if you do it correctly, it could have a very strong effect, reducing methane lifetime and reducing concentrations in the atmosphere.
When we looked at how to find the best solutions, we realized that there were just 3 criteria required. That a viable solution has to be permanent. If the carbon isn't sequestered for at least 100 years, it's not a viable solution. It needs to be scalable to pretty much the level we need, which is 60 gigatons per year. And it needs to be financially viable, because it's one thing to have a good idea, but if no one's going to pay you to scale it up to 60 gigatons a year, it's simply not going to happen.
The field of methane removal research is growing, and inevitably there comes a point where at some level science and business converge. Blue Dot Change is a startup company based in California's Silicon Valley.
So one thing that concerns some people, that's totally understandable, is that we're a business. And so why did we become a business? Business provides us an opportunity to do certain things that are harder to do in a setting like a university setting. For one thing, we can have a more reliable funding stream so that we can concentrate on the work we need to do, the science work we need to do, and the social outreach we need to do to make sure that we're on track without continually be writing grants and having the feast or famine of the grant environment.
With aerosol-based methane removal processes, partnerships will become more and more important as the science moves towards finding methods of delivery, which may be as challenging as the science itself. Whether it's the possibility of partnering with shipping companies or the development of ocean-based towers, the ideas are as varied as they are at times exotic.
We need big structural changes, yes, to reach 2050 climate neutrality, but we cannot wait for 2050. We have to cut emissions fast. And methane is one of the gases we can cut fastest.
To date, 150 countries have signed on to the Methane Pledge, in which they commit to collectively reducing global Anthropocene methane emissions across all sectors by at least 30% below 2020 levels by 2030. This is a huge step in the right direction if the underreporting of emissions is addressed and the succession of ever-changing governments are able to maintain their commitments.
The methane treaty should also include methane removal. So if we can perfect the chemistry and the physics that we know how to do for methane removal, that could be the single most important lever, along with methane mitigation, to cool the world in the near term.
For some reason, humanity seems cursed to find the simplest of solutions to be the hardest ones to implement. The science and process behind using aerosols to remove methane is complex, but there are also many simple approaches to addressing methane that can be done today that can make a real impact well within the coming decade. The restoration and protection of ecosystems such as wetlands has an enormous role to play in stabilizing methane emissions. A warming climate is already playing a part in the increase of wetland methane emissions, but the disturbance of wetlands to make way for development can seriously increase these emissions. Protection and good management of soil has major benefits too. Microscopic life that lives in soil, or microbes, play a major role in absorbing methane as well as producing methane, so enhancing the good methane-absorbing microbes and reducing the microbes that produce methane can make a real difference. Around 25% of farmland soil is deficient in iron, which leads to plants suffering from iron deficiency. Spraying crops and soil with iron sulfate increases crop yields and improves microbes' ability to absorb more methane. This includes rice crops, which provide up to 70% of half the world population's calories. For livestock, it means reducing our appetite for meat, decreasing the global livestock population, using food additives that reduce methane burps, and treating livestock barns to capture methane before it's released into the atmosphere. For landfills, if we significantly reduce the millions of tons of food we waste and send the food that is discarded to compost sites instead of landfills, and then covering landfills with biocovers to capture methane and flare the residue. For oil, gas and mining industries, it means safely retiring equipment, plants and mines, properly maintaining pipelines and fixing leaks, coating large surfaces like the sides of buildings, windows, wind turbines with zeolites, which are porous minerals that trap methane in microscopic pores, oxidize the gas, breaking it down into carbon dioxide.
Well, we spend most of our time trying to stop methane emissions today. I work in homes looking at appliances like stoves, furnaces, and water heaters. And stoves, for instance, not just release methane and greenhouse gases into the atmosphere, they release indoor air pollutants like NOx gases and hydrocarbons that we breathe that triggers asthma and other diseases. So I want everyone to think of climate solutions not just as helping the environment, but improving our health.
One of the not-so-natural ways of removing methane is a method used extensively by the oil and gas industries: flaring, where excess methane is burnt rather than storing it or releasing it directly into the atmosphere. Throughout the world, there are disused oil wells and mines that continue to leak methane long after they've closed down. Frost Methane, a climate restoration startup, is addressing these leaks through the development of a compact flaring system that can be installed, operated, and monitored in remote locations.
So my name is Oli Razak, and I run an organization called Frost Methane Labs, and we find concentrated, continuous, unregulated sources of methane and install devices to mitigate them. And just burning it is basically the cheapest mitigation you can imagine, because it turns one molecule of methane to one molecule of CO2, and it's extremely low cost, and it is reasonably, compared to some of the other solutions, it is reasonably easy to do in a very robust way. So we take methane that otherwise would have made it out into the atmosphere, right? So it's coming through cracks in the ground, it's coming through lakes, it's coming through old water wells. So this is methane that is not economical for oil and gas companies to capture. If it is, fantastic, right? Putting it in the pipeline is always better than setting it on fire without a productive use, but often it's not possible, right? Because the pipeline is too far, the quantities are too small. And so what we do is we build these devices that set it on fire, but the methane that's coming out from our sources is pretty different than what's coming out of your stove. I mean, it's still methane, but it's methane that comes with nitrogen and CO2 and sulfur. So our device needs to be able to handle the variety of flow rates and the variety of gas compositions that come out naturally.
Back in northern Alaska, Frost Methane is exploring whether the technology they're using to flare escaping gas from mines can be modified to capture and flare methane being released from lakes. Major amounts of methane are being released into the atmosphere from the decomposition of vegetation, as well as recently discovered thawed passageways that reach hundreds of feet down and are now releasing fossil methane too.
A lot of methane is coming out of these lakes, and the way that it's coming out is by bubbling. That's important because there are other microbes that can eat methane, and that would be a good thing, but the bubbles move so quickly up through the water column that other microbes don't have time to eat the bubbles. Those bubbles come to the surface of the lake, and they pop, and they're putting 80–90% methane that was in the bubble straight into our atmosphere. And once that methane molecule enters the atmosphere, it just takes 1 year for it to circulate around the whole planet. So methane coming out of the Arctic spreads around the entire world and contributes to global climate warming. Yeah, this is a homemade methane bubble trap. It's got a plastic bottle a tube, a stopcock, and then a plastic skirt with a ring around it. And bubbles that are leaving the lake sediments rise up and they go into this trap and they get funneled into the bottle. Methane is natural gas, so it's flammable, and we collect samples and bring it back to the laboratory to measure the exact concentration. But very often when we're in the field, we can do a flame test just to make sure that the gas we have is methane. So I am going to push the bottle underwater to pressurize the gas, and then we'll light a match. And if it's methane in here, the flame coming out of the stopcock should get bigger. If it's not methane, then the fire on the match will go out. We've got methane. If you look at a map of the Arctic, you'll see that there are millions of lakes. All the lakes emit methane, but most of the lakes emit a lower level of methane. It's these new lakes, these lakes that have formed recently from permafrost thaw, that are emitting the highest amounts of methane. And that is because the freezer door has recently been opened. So the microbes are having their feast. These lakes are the key to understanding the future. Models suggest that the majority of surface permafrost in the Arctic will be strongly thawed by 2100. What models do not take into account is the formation of these lakes. And when these lakes form, the water heats the ground and thaws at orders of magnitude faster. We get deep, fast, abrupt thaw. And so the carbon that's very old, deep beneath these lakes, becomes food to microbes that are generating methane that's bubbling out of the lakes. And the impact is that it will double the permafrost carbon feedback. So what scientists had thought before for emissions from permafrost carbon on land will be at least 2 times higher because of the formation of these lakes and their potent methane emissions.
Greenland, sitting in the Arctic blue sea now during those 3 summer months, is losing its ice irreversibly, and when all of it is gone, 6.5 meters to 7 meters sea level rise. And also, now this is important, permafrost on the land mass around the Arctic Ocean, the North Pole being roughly in the middle of the Arctic Ocean, permafrost is now losing methane explosively.
We don't focus on the scary outcome of a methane burst, in large part because the science is uncertain. But if I knew there was a 1% chance of a catastrophe happening and we were not prepared for that 1% chance, although we could have been, you know, again, this is what we weigh in terms of what is the moral, what is the ethical thing to do. To be prepared for a worst case disaster scenario, absolutely.
Being prepared for a major increase in methane emissions will have to include methane removal. But as in all scientific work, the risk of unforeseen circumstances is present. But the risks associated with doing nothing may be far greater.
The less we do, the better, and we want to be in line with the precautionary principle and not cause any additional harm. That being said, humanity is conducting a huge experiment with the Earth's climate right now. And this is going to cause the planet to go outside of where it's been historically. And some of the implications are very bad. We might like to avoid that.
As politicians negotiate methane reduction targets that either don't reflect reality or become diluted due to pressure from special interest groups, we have to keep moving forward with real goals and real solutions. Climate restoration, the removal of historic man-made gases, may be the missing link to saving the climate, but it has to be applied with real reductions of emissions, the protection and restoration of natural habitats and resources, and maybe most important of all, for humanity to acknowledge the issue and to commit to action.
There's no one solution here that's going to solve everything, and this is all about adding new tools to our toolbox so that we can have a more robust climate response and mitigate the many different flavors of risk that we unfortunately face today.
I've been accused of being oversimplistic and too optimistic by scientists, and in a sense, in a scientific sense, that's correct. That is, science is about predicting the future based on the past, and in fact, the future is not written yet. We get to write it.
We have an enormous amount of work to do. We, as humanity, have an enormous amount of work to do. And when I had that conversation with Peter, I felt hope. Maybe we could do something. And I dropped all my other work, which was interesting work, to say, I really need to work on this because I am well suited from my background to work on this very project. And I wish to keep breathing for 20 years.
Goals are essential, but to achieve them we need to develop a shared vision of what the world could look like if we all work together restoring the climate. Culturally, the narratives need to move away from disaster fantasy to stories of a world where things could go right. Practically, we all need a clear understanding of what the choices are.
You know, climate restoration makes a whole lot of sense, first of all, because it's win-win, you know, healthier ecosystems, a healthier environment, thriving forests. A better planet is obviously better for us and all other living things. And so it's a no-brainer to try to restore our environment as much as we can to a functioning, you know, global ecosystem.
So here we are, out of road, out of time, but not out of ideas or science or resources, to restore a world that has been so badly damaged by our inventiveness and insatiable appetite for more. Climate restoration, in conjunction with all the other tools at our disposal, offers a real pathway, but the window of opportunity is short, so we have to support in every way possible the fight to restore the climate for ourselves and all life that follows.